of it and you want to create an orthonormal basis for it. So what to do? So what you can do, try to figure out only two vectors that are orthonormal. So what you can do, that using these two vectors, you can extend these two vectors and you can create the other, what do you call, 8 vectors that all together will form a basis of inner product space, not only basis but orthonormal basis. So this is something interesting, that I have 10-dimensional vector space or n-dimensional vector space, and I know that in that vector space there are only few vectors. There are few vectors which are orthonormal. The question is, can I extend that set of orthonormal vectors to a basis of the inner product space? The answer is yes. And the answer, let me write this precisely in the form of, what do you call, in the form of a corollary. In the form of corollary. So every finite dimensional inner product space. Okay, now every orthonormal system, so imagine you have an orthonormal system in a finite dimensional vector space. You can extend this orthonormal system in a finite dimensional vector space, again and again. Inner product space can be extended to an orthonormal basis. Okay? So here's the thing. You have a finite dimensional inner product space and you have some orthonormal vectors. Then you can take some orthonormal vectors and extend them. In other words, you can add some more orthonormal vectors to them, okay, which are unknown, and turn them into an orthonormal basis of V actually. Okay? In the orthonormal basis of V. So how are we going to do it? How are you going to do it? So imagine you have been given an orthonormal system. Imagine let V, the vector space V, inner product space V is n-dimensional. Okay, is n-dimensional. Let's assume that. And let V1, V2, Vr, where R is some number that is smaller than n, is an orthonormal system. system. Okay? Then what? Is an orthonormal system. Question: can I extend this to the orthonormal basis? The answer is yes. Why? Because from your first linear algebra course, you know very well that if you have, for example, a 5-dimensional vector space in which you have 3 vectors that are linearly independent, okay, then you can find 2 more vectors and put them together that can form basis for what do you call the vector space. So let's take v1, v2, vr. They are not only orthonormal vectors, but they are vectors in the inner product space V. And then this v1, v2, vr can be extended, to a basis. Okay. So I'm not going to get into the details of it, that how to add some more vectors in a given set of vectors to form what do you call a basis actually. So another thing that is obvious is that since this is an orthonormal system, so all of these vectors must be linearly independent. So what we can do in these linearly independent vectors, from the linear algebra that you learned in your first course, what you can do, you can extend this what do you call basis, extend these R vectors to a basis that comprises of n vectors. V2, VR plus 1 and up to Vn. So you can do it of V. Question: Is it necessary that all of these vectors are this n vectors that you have extended, okay, are R vectors that you have extended and formed a basis for V? It is also an orthonormal system. The answer: there are 2 possibilities. Either this is going to be an orthonormal system. So if it is an orthonormal system, in other words, V1 to VR, I already know that it's orthonormal system, and I added some more vectors to it. Now there are 2 possibilities for all these n vectors, that either it is going to be an orthonormal system. If it is an orthonormal system, this is already orthonormal basis actually that we want. But the other possibilities could be that, okay, I know that V1 to VR are orthonormal, but this entire system, this entire set of n vectors does not form an orthonormal system. So what you can do, you can take this system and apply what do you call Gramschmidt. What do you call Gramschmidt? Okay, and create an orthonormal system to V1, V2, Vn, and construct an orthonormal basis, or orthonormal basis, say U1, U2 up to Un actually for V. Okay, but here's one little glitch. I wanted to extend this system. These might be the new vectors actually. I don't want a new basis, an orthonormal basis for what do you call inner product space. I want to extend these vectors. In other words, in this list, I want to add some more vectors that are orthonormal. But we just discussed actually that if your vectors are already orthonormal and you apply Gramschmidt on them, there will be no difference actually on them. So nothing will change in them. So in other words, if you take Gramschmidt process and apply Gramschmidt process on what do you call V1, the Gramschmidt process will give you the same, and obviously I can take what you call the vector V1, and by applying the Gramschmidt process I'm going to get what do you call U1. But since V1, V2, Vr is a part of what do you call an orthonormal system, so this U1 is not V1 is not going to change. In other words, this U1 is going to be the same V1. In other words, the Gramschmidt process is not going to change these vectors V1 to Vr. So the V1 to Vr would stay same. In other words, your U1 is going to be same, your U2 is going to be same as V2, and up to your UR is going to be VR. Okay, and hence the new vectors UR plus 1 up to UN, these will be maybe different from what do you call VR plus 1 up to Vn. But the first R vectors under the Gramschmidt process are going to stay same, because we know that for when you apply the Gramschmidt process on an orthonormal set of vector, it does not change, it just returns the same vectors, because the orthonormal vectors are already orthonormal. So the Gramschmidt process is not going to do anything. Hence, what happens is that your new bases, new orthonormal bases that you have found U1, U2, Un is basically this V1, V2 up to VR and UR plus 1 up to UN. So in other words, I took my orthonormal system and I added some more vectors to it, and I found an orthonormal system that is also a basis for the inner product space, and hence this basis is orthonormal basis. Orthonormal basis. Okay? I know in this first part of discussion I'm doing a lot of waving of hands, because I'm assuming that you know the linear algebra, the first linear algebra course very well, and you know the Gramschmidt process. So I'm not spending too much time on it actually. Okay? So what is the conclusion in this this section? We defined what is orthonormal system. Okay, what do you mean by orthonormal system? We did some examples of it. We showed that orthonormal systems are linearly independent, and then we showed that the key result is every finite dimensional vector space, inner product space. So if you have a finite dimensional inner product space, that inner product space has an orthonormal basis. And then finally we showed that if you take some number of orthonormal basis vectors in a finite dimensional inner product space, you can cleverly add some more vectors into those orthonormal vectors and create an orthonormal basis for the entire vector space actually. Okay, so this is a set of discussions that we have done so far, and now I would like to move to the next session. The next section, and in this section I'm going to get into the details of every single thing. Okay. So I keep on saying to everyone, really, the over 90% of mathematics is linear algebra. So, you know, and learning linear algebra never ends actually. So you always learn new things, new stuff in linear algebra. So try to learn as much as linear algebra you can actually, because really the linear algebra is the soul of mathematics. Okay. Even you can write the entire calculus in the terms of linear algebra, and that's what makes linear algebra very important. So it just, you know, jumps into the, you know, all areas wherever the calculus is applied, for example. But this is just one application. There are many more than this. Okay. So what is the next topic that I would like to get into? So this section is about the Riesz Representation Theorem. Riesz Representation Theorem. So you will see that if you have an inner product space with an orthonormal basis, so the inner product space with the orthonormal basis. So the most of the time now on, whenever we're going to discuss an inner product space, we will always consider an orthonormal basis of it, because we just proved, or we just saw that every single, you know, inner product space, or finite dimensional inner product space, always have an orthonormal basis. So we're going to make our life easier and always consider the orthonormal basis. So let's start with what you call a new class of linear transformation called the linear functionals actually. Okay? Linear functional. Linear functional. Okay. So what are the linear functions? Here's the definition. So let V be a vector space over a field F. Okay. Then a linear transformation. Okay. Then any linear transformation formation F, okay, or maybe phi, you know, any symbol you like, from the vector space. This is important. From the vector space, not to another vector space, but to its field. And by the way, we know that every field is a vector space as well. Okay? So a linear transformation from a vector space to its field, you call such linear transformation as a linear function. You call that linear transformation as linear function. Okay? You call that linear transformation as a linear functional. So what's a linear functional? Linear functional is a linear transformation from the vector space, whatever your vector space is, to its field. Okay? This is what. And what we will do basically in this theorem, or in this section, is that if you consider the vector space as an inner product, you know, space with an orthonormal basis, then any linear functional can be written in a very interesting manner, okay, in the terms of the inner product actually. So it kind of classifies all kind of linear functionals. So all linear functionals on a finite dimensional inner product space, and hence it's also true in infinite dimension, can be written in a very simple form actually, in a very particular form in the terms of the inner product. So we're going to get into that. So let's do some examples of linear functionals actually. Okay. So for example, the first example is that you take any inner product space. So let V be any inner product space over F. So any inner product space. So it could be, so this means that this V can be Rn, it could be Cn, it could be the space of all matrices, it could be C01 or CAB, okay, it could be L2AB, it could be anything. So we discussed all such examples and many such examples in the chapter of inner product space. So imagine you have any inner product space, okay, then in that inner product space, imagine you take a fixed W, so a vector W, okay, whatever. That W in V is a fixed element, okay. Then corresponding to this fixed element W, you can define a linear functional. Let's give this linear functional a name W, phi W. So phi W is going to be a map from V into what do you call field F, and the definition of the phi W operated onto V is going to be what? Just compute the inner product of V with this fixed element W for all V in V. Okay? For all V in V. Then this phi W is a linear functional. Is a linear functional. Okay? So this is a very interesting observation. To every element in the inner product space, you can always find a linear transformation. So corresponding to every element in vector space, you can always find what you call a linear functional. Okay, and then when we will move ahead, we will see actually that the collection of all such linear functionals. So for every element in inner product space, you have a linear functional. So the collection of all such linear functionals also becomes a vector space, and you call that vector space as a dual space actually. So I'm not going to get into that, but for now what I did, take W, and using this fixed W, I can define a map that depends on W such that phi W operated onto any V is going to take the inner product of the V with this fixed element W. Okay? So in other words, take W and take the inner product of W with every single element in the V. That map is going to be a linear functional. So why it is going to be a linear functional, it's not difficult to say. And then we're going to get into some concrete ways of it. Concrete situations actually. Okay. So to show that this is a linear transformation, I need to apply it onto say some vector AU plus BV. Okay. where A and B are scalars and U and V are vectors in the inner product space V. By definition, I can write this as AU plus BV and its inner product with fixed W. Then by properties of inner product, I can write this as A UW plus B VW, and hence this will become A phi W of V plus phi W of U plus B phi W of V by definition. And obviously this shows that this map phi W preserves the addition and the scalar multiplication of the inner product space or the vector space actually, and hence this is a linear transformation. Okay, let's take this V in what do you call in some concrete situations actually. Okay, let's take this V and take it into a concrete situation. For example, let's consider this linear functional here actually in CAB. So let's take, for example, let's take, say, for example, f of x to be, let's take f of x to be, for example, where x is in the interval a to b, to be some function. Okay, some function. So I don't know, let's call it x actually. Okay, so let's call it x, where x is in, what do you call, AB. So it's a polynomial x. X is in the interval a to b. Okay. So what would be the inner product corresponding to this f? So phi for w. Okay, so I must write more explicitly that I'm considering V to be CAB, okay, space of all continuous functions defined on an interval a to b. Then we know that on this interval we have this inner product, which is simply the product of say f of x, g of x, dx. In other words, multiply and take their integral, okay, because f and g are continuous, their product is continuous, and hence, you know, for continuous functions, the integral makes sense, so inner product makes sense. You can prove that this is inner product. And now, I want to take, for example, a particular function. Okay, so, for example, I want to take, say, f of t, or f of t equal to, maybe f of t equal to, what do you call, I don't know, take any function, say t. Maybe t squared, something like that. Okay. Then an example of linear functional corresponding to this function t squared, f operated onto some g, is going to be what? That take the integral from a to b and multiply the f, take the inner product of f with g, which means that take f of x and take g of x dx, so it's going to be a to b, okay, and you're going to have a t squared g of x dx actually, no, x squared g of x. So this is what is going to be. So this is a linear function, okay, and the interesting case also would be that, for example, when you take f of x equal to 1 actually. So what would be the linear transformation that is corresponding, linear functional that is corresponding to this f? So by definition, by f of g. So by definition, this is going to be equal to the integral from a to b of g of x dx. So what does this shows? This shows something interesting, that your definite integral, so this is a simple definite integral of g. Your definite integral is basically a linear functional actually. Okay, your definite integral is a linear functional. Okay, so linear functionals are not something new. You already know them. Integrals, especially the definite integrals, are what do you call an example of linear functionals actually. Okay. So linear functionals are one of the most important objects in the entire mathematics, especially they